Hey, so we're going to do the last part of our antiderivatives lesson before we start the next phase of this chapter. So I want to review with you some notation, vocabulary concerned with sequences and series because you can get a little bit bogged down in this stuff when we start tomorrow's lesson. So let me break it down a little bit so I don't throw it all at you at once, okay? So remember, a sequence is just a string of terms separated by commas, and they generally follow a mathematical pattern. So a sub 1, comma, a sub 2, comma, a sub 3, yada, yada, yada. A series is not just the list of terms, it's the sum of the terms. So I'm going to say a sub 1 plus a sub 2 plus a sub 3. Remember that you have a subscript down here, I, which shows you what your variable is going to be. And so a sub I. And then you have a lower subscript 1, which says start with a sub 1. And then you have an upper superscript, which tells you to go all the way to a sub n and then stop your addition. So sigma, the Greek letter, is the mathematical notation for summation. I is the index, 1 and n are the upper and lower bounds. Okay, so let's take a look at this problem. Now let me remind you, we talked about this last year, that there's always multiple ways to write summation notation when you're doing something like what I'm fixing to show you. So there's more than one way. On this first problem, I would probably keep it simple. And I would say, okay, let me call the terms 1, 2, 3, and 4 the first, second, third, and fourth term. And I can see that a sub I is going to just equal I. So a sub 1 is 1, a sub 2 is 2, a sub 3 is 3. So then I've got what I need to say that the summation goes from I equals 1 to, well, since it says a sub 4 plus dot dot dot, it's going forever, so my upper bound is infinity. And I'm just going to say of I. That's it, because I'm summing those terms of the sequence. Now, on this next problem, if I start out the same way, I'm going to say this first term is a sub 1, this is a sub 2, this is a sub 3, and this is a sub 4. Okay, if I manage it this way, then a sub I is going to have to be, it looks like I'm going to have to take I and add 2. So like for instance, I'm going to take 1 plus 2 and get 3, and then 3 squared is your 9. Or if I say a sub 2, it would be 2 plus 2 is 4, 4 squared 16. So that's the formula for my sequence. So then when I go to write the sum, this time I'm going to start with 1 and go to the fourth term because I have a finite number of terms. And then I put the terms of the sequence after that. So if I just have a sub I equals, then I write the sequence with commas. If I sub out the a sub I and put a sigma in front of it, then I write the summation, the series with plus signs between. Now let me mention on the problem we just did, somebody else might say, no, that's not the way I want to write this. And remember, there's always infinitely many ways to write these. And you're going to wind up, you'll see as we get deeper into what we're doing, there's usually 2 to 3 best ways in what we're doing, and you'll need to be able to recognize you might have done it one way, but the correct answer in a multiple choice set is another thing. All right, so if I reset and say this time I want to be adding the third, fourth, fifth, and sixth terms, then it simplifies my a sub I. Now I can say a sub I is just I squared. So a sub 3 is 3 squared, a sub 4 is 4 squared, and so on. Then my sum goes from 3 to 6 with my sub and superscripts, and then I just put I squared after the summation. So just reminding you of that little bit. We will be writing sums, but not exactly like this. It's going to be embedded in something bigger. So if I ask you to evaluate these sums, just realize that this problem means you're going to add the fourth, the fifth, and the sixth terms. How do I know that? Because it's saying go from the fourth term to the sixth term. That's your upper and lower bound. So the variable is k in this part. So k is going to start with 4. So it would be 4 factorial. It's going to scroll to 5, and that would be 5 factorial. And then it's going to scroll to 6, and that would be 6 factorial. Remember, 4 factorial means 4 times 3 times 2 times 1. 5 factorial means 5 times that 4, 3, 2, 1, so 5 times 24. 6 factorial means 6 times that 5, 4, 3, 2, 1, so 6 times 120. And then you just add the numbers and you've evaluated the series, or you've evaluated the summation. And you'll kind of hear those words interchanged. So on the next problem, I'm going to do the same thing. I'm just going to say, well, the problem tells me that I'm going to add the 10th, the 11th, the 12th, and the 13th terms. So J is my variable, so it varies from 10 to 11 to 12 to 13. So when I start out, plug in 10. So 10 minus 5 is 5 cubed. Plug in 11 now. 11 minus 5 is 6 cubed. Now plug in 12. 12 minus 5 is 7 cubed, and then 13 minus 5 would be 8 cubed. And of course we know 125, 216, 343, 524, 512, my bad. Sorry about that. And then we're going to add. So let's see here. I've got my calculator out. I'm just adding. So I'm getting 1196. Okay, so I double checked. Now we're going to do this same kind of thing, and we're going to look at two different methods. So our first method is going to be doing what we've just been doing, just straightforward, add the terms it says. So on this first one, if I is, do you see on the first one, I'm going to say a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. And so I'm not going to write that now. I'm hoping you're seeing that I'm going to kind of start to wean out a step. So on this one, a sub 1 is just 1. A sub 2 is just 2. A sub 3. A sub 4. A sub 5. A sub 6. 7, 8, 9, and 10. So when I add, I notice I could do 1 and 9 is 10. 2 and 8 is another 10, so that's 20. 3 and 7 is another 10, so that's 30. 4 and 6 is another 10, so that's 40. And then I've got 45, 55. Whew, goodness, I tell you what. Let me, on this next one, let me make this a little simpler. Let's say that the superscript is just 5, because I think you could see it without going on and on and on with it. So on this one, notice that there's no variable in the sequence part of the problem. It's just the number 6. There's no variable. So the first term is 6, and so is the second, and so is the third, and so is the fourth, and so is the fifth. So 5 sixes would just be 30. So that says it doesn't matter what you plug in for n, the value of the term stays 6. So on the next one, a sub 1 would be 1 squared, a sub 2 would be 2 squared, a sub 3 would be 3 squared, a sub 4 is 4 squared, a sub 5 is 5 squared, a sub 6 is 6 squared, and a sub 7 is 7 squared. So when I add all those up, let's see, I'm going to get 20 right there. Let's see here, 30, 30 and 25 is 55 plus 36 plus 49. I'm getting 140 there. All right, last but not least, the bottom problem, the first term is 1 cubed. The second term is 2 cubed. The third term is 3 cubed. The fourth term is 4 cubed. And the fifth term is 5 cubed. So again, I just add. Let's see here. I'm going to say 1 and 64 is 65. 65 plus 125 plus 8 and 27 is 35. So I'm getting 225 on this one. $224. Let's see here. I'm double checking. See what I said wrong the first time. Nope, 225. Okay, I just wanted to double check. Now, if you look beyond, I'm going to remind you that there are 3 special summations that you've seen already. So those 3 that you've already seen is, first of all, that if you want to sum a constant term over and over and over again, you just multiply the constant term times the number of terms. So the constant term times the upper bound. Now, where did we see that one? Right here, the second problem. Since we summed 6 5 times in a row, we could have just said the upper bound times 6 is 30. All right. Now, your second one that you've seen before is the sum of just counting numbers. So if I'm summing just 1 and 2 and 3 and 4, I'm just summing counting numbers. And so the formula is, I've got U for upper bound. A lot of times people will put I where I've got N, and they'll put N where I've got U. But I like to put the U on the top because it helps you remember upper bound. So the formula is strictly upper bound plus 1 times 2. Over here, that would have been problem 1. Okay, so I could have said, oh, I'm summing the first 10 counting numbers. So the formula is the upper bound times the upper bound plus 1 all over 2. So of course 2 goes into 10 5 times. 5 times 11 is 55. So I get the same thing. Then I also, the third formula that you saw in Algebra 2 and Pre-Calculus is if you're summing the list of perfect squares. And so again, upper bound plus 1, double the upper bound plus 1 all over 6. These formulas are just memorized, ready, okay? So of course that goes with my problem 3. So I'm going to say, oh, I'm summing the first 7 perfect squares. So my formula is upper bound plus 1, double your upper bound, so 7 times 2 is 14, and add 1, and all over 6. So I'm putting that on my calculator. 7 times 8 is 56 times 15, all divided by 6 on my calculator. And sure enough, I'm getting 140. So I'm double checking where I listed and added manually. So clearly on problem 4 here, I'm going to use the last formula. Guys, this one you've not seen before. It's new, but it's easy. And let me show you something else. A lot of times, instead of memorizing it as u squared, u plus 1 squared over 4, some people will look at it like it's this formula, u plus 1 all over 2, quantities squared. It's the same thing, and that tends to be what I do. Okay, so my second and fourth formulas are very, very close, which is pretty cool. So if I recognize that I'm summing perfect cubes, I can say, oh, okay, so do upper bound plus 1 all over 2, and then square that because I'm actually summing perfect cubes, and that's the formula. So 5 times 6 is 30. 30 divided by 2 is 15. So this becomes 15 squared, and 15 squared does equal 225. So yay. All right. So that's just an overview of your formulas. And then we're going to do a couple of practice problems. Okay. So the first problem The idea is, and I can go over this more fully, and if you want me to, just log on and we'll do it together on Zoom. But the idea is to say, well, let me break it down to where what I'm doing is breaking this into the sum of the first 50 perfect squares, and then 3 times the sum of the first 50 counting numbers. And then I'm going to subtract 11 50 times. Now normally I don't write all the first step out. I'll be happy to show you about why I can do that. I didn't want to make your video too long here. But on this one, I'm going to say, well, the sum for the counting numbers is the upper bound. The sum for the perfect squares, my bad. Upper bound times 1 plus 1. Double the upper bound, which is 100 plus 1, all over 6. On the next one, I'm going to say 3 times. Now I'm going to sum the first 50 counting numbers, so the upper bound plus 1, all over 2. Then I'm going to subtract 50 11s. So I set it up. Now I'm going to begin to calculate. So when I do 50 times 51 times 101 divided by 6, and I'm just doing this on my calculator right now, I'm getting 42,925. So on the next one, I'm going to say 3 times, since 50 divided by 2 is 25, 3 times 25 is 75 times 51, and that is 3825. And then 5 times 11 is 55 times another 10 is 550. So 42,925 plus 3825, and then minus 550 works out to be 46,200. That's what I'm getting on my calculator. I hope you're doing these on your calculator too, so you can see where this is coming from. Now, I can separate summations with just by adding and subtracting. I can also, you can see right here with the 3, I can pull a plain number to the first or the front of a summation, okay? But I can't do this, okay? A lot of people say, oh, well then do I equals 1 to 32 of I times I equals 1 to 32 of I squared plus 1, okay? So you can't do that with summations. You can only separate out parts where you're adding and subtracting the individual parts. So this won't work. That's a no, you can't do that, all right? So what I have to do instead is say, let me see if I can't rewrite the problem, and I can. If I just simply say, well, let me distribute, and then I've got I cubed plus I, and then I can separate it into I cubed plus I. So you're allowed to separate parts if all you're doing is summing. So if you're adding or subtracting 2, because subtracting, of course, is just adding a negative. And you're allowed to separate the parts as long as you're just pulling a number that you're multiplying by the variable expression. So now I've got it back in familiar terms. And so I'm going to say, okay, to do this, I know for the I cubed part, that would be summing the first 32 perfect cubes. So I'm going to say upper bound plus 1, all over 2. And then I've got to square that guy. And then on the second part, well, it's the same thing. It's the me summing the first 32 counting numbers. So it's upper bound plus 1, all over 2. So let's see here. 32 divided by 2 is 16, so that's 16 times 33. So I'm getting 528 squared plus 528. That's how that would work out. And so when I do that on my calculator, I'm getting 279,042. Now, I have not been able to find any online problems for you to do this, so I'm going to assign problems out of the book like I would have. If you don't have the book at home with you, I want you to get online with me and let me know so that I can provide some pictures for you, okay? But I don't think we're going to be able to get around doing some of that stuff online out of the book if we really want to do our best job, especially for those of you all that are still headed toward the exam. So let me remind you, I want to just show you a couple of things, okay? I want to remind you that you know the derivatives of the arc trig functions. The big ones are that the derivative of arc sine x equals 1 over the square root of 1 minus x squared. I know it's been a while. The derivative of arc secant x is 1 over the absolute value of x, and then the square root of x squared minus 1. And I always remember that the one that leads with x on the outside leads with x on the inside. So that's how I remember the secant x has the x squared minus 1 instead of the 1 minus x squared. And then the derivative of arc tangent x, this is my favorite one, equals 1 over x squared plus 1. So I'm mentioning those three. Remember, the derivative of arc cosine is just negative 1 over the square root of 1 minus x squared. I'm not going to ask you about those so much in relationship to our new material, because if someone said, well, I'll show you in a minute. Let me remind you that now I know the related rule that the antiderivative of 1 minus x squared dx would be arc sine x, and of course plus c. I don't want to forget that. But let me mention what I was just saying. The reason I'm not emphasizing the derivatives of arc cosine, arc cosecant, and arc cotangent is that if I had given you this problem and I had said negative 1 over the square root of 1 minus x squared dx, most people would pull the negative outside the antiderivative sign, outside the indefinite integral sign. This would be what most people would do with this problem. And then they would say, oh, that's negative arc sine x plus c. Now you could say arc cosine x plus c, but I don't think that would be as common. So that's why we're not going to focus on that kind of thing as much. We're just going to use the kind of the big three that turn out positive. I think that would be most people's strategy. All right, so similarly, I could say that here you've got 1, if I say what's the antiderivative of 1 over the absolute value of x times x squared minus 1 dx, you're going to say, well, that's arc secant. And what's the antiderivative of 1 over x squared plus 1? Again, you're going to say, well, that's arc tangent. So I want to just mention a couple of kind of problems that I can make a little fancier. I don't want you to be taken off guard with these. If you had something like this, if I said, what is the antiderivative of 4 over the absolute value of x? Then I want you to realize you can pull the 4 because it's just a plain number outside the antiderivative sign. So you're really just taking the antiderivative of the variable bar and multiplying by 4. So you would say, okay, that's 4 arc secant plus c. Okay? Now, similarly, if I said, what is the antiderivative of 1 over 3 times the square root of 1 minus x squared dx. I would do the same thing. I would pull the 1/3 out and then look at it this way. And you'll see some others like that too. I'll mention to you in just a second. But there, I would say, okay, so that must be 1/3 arc sine x plus c. Now, one that's similar to like what I just showed you, if someone said, what is 1 over, we'll say 7x. All right, a lot of people will make this one harder than it needs to be. Pull the 1/7 out and just look at it as the antiderivative of 1 over x. Now, do you recognize what that would be? We talked about that on Friday. All right, I want to show you one more, and then we are done, okay? So this is kind of a fancy pants problem. I can construct problems that require me to separate fractions. So if I looked at this point, there are different ways to do this, but you're going to be like, whoa, what's going on? So consider that I could do this. I could say this is x squared plus 1 over x squared plus 1 and x squared plus 1. And you might say, why in the world would you do that? At this point in your development, you probably wouldn't think to do it on your own necessarily, but you need to start looking for tricks like that. Then I'm asking you to simply take the antiderivative of 1 and the antiderivative of 1 over x squared plus 1. So what is the antiderivative of this 1? Just x. What's the antiderivative of 1 over x squared plus 1? Oh, that I've got memorized as arctan x. And then, of course, your plus c. So keep your eyes out. There's going to be one in the homework for today that has something to do with separating fractions like that. And we're done. I'll see you tomorrow. We're going to really be getting into the next big topic where we'll use summations heavily.